College Board optimization problems. Can't wait, let's go. Number 1. Okay, so here we're given let g of x be x e to the minus x plus b e to the minus x, where b is a positive constant. For what value of b does g have an absolute max at x equals 2/3? Remember to justify your answer. Okay, so I actually am going to do a little algebra on this first, and I'm going to factor out that e to the minus x so that I have x plus b here. Now, in order to find an absolute max, I know that I need to look for the first derivative equal to 0. So what will that first derivative be? Well, it means I need to take the derivative with the product rule. So g prime is going to be negative e to the negative x times x plus b times the derivative of this. The derivative of this is 1. Derivative of that is 0 times this e to the minus x. So again, I'm going to factor out an e to the minus x, and I'm going to get left over this negative, this x plus b. That's supposed to be a plus 1 then, and a plus 1. So I have negative x minus b plus 1. So here's g prime. Now this part of g prime is never equal to 0. This is exponential decay. It has a horizontal asymptote at 0. So this is the only part that can be equal to 0. So we're saying negative x minus b plus 1 should be equal to 0. And we know that x equals 2/3. So if we plug a 2/3 in here, I've got negative 2/3 plus 1 minus b equals 0. I get 1/3 equals b. All right, now I know something's happening at 1/3, but I don't know a max or a min yet, and so I still feel like I need to check that. So let's make our little sign chart and put our 2/3 here. And we'll look at this g prime function here, e to the minus x. Negative 1/3 plus 1 is 2/3, so 2/3 minus x. Okay, so here's g prime. This is our g prime sign chart. If we plug a 0 in here, we end up with a positive times a positive. If we put in something bigger, like 1 over here, 3/3, 2/3 minus 3/3 is negative 1/3. So negative times a positive is a negative. And so I can see I have a max at 2/3. Now, there are no endpoints for a bounded interval here, and there are no other critical points. So this max has to be the absolute max. And I would say there is a max at, or better yet, the only max is when b equals 1/3, because to the left of x equals 2/3, g prime is greater than 0, and to the right of x equals 2/3, g prime is less than 0. Since there are no other critical points and no endpoints, this is the absolute max. And you shouldn't probably write that correct. Okay, there's problem number 1. Let's take a look at problem number 2. This is a little more thought-provoking, I find. We've got a rectangle. One side has its upper vertices on the graph of y equals cosine x. What is the minimum shaded area? Well, the minimum shaded area is going to occur when we have a maximum white area. So when the area of the rectangle is largest, that's when this shaded area will be smallest under that arc. So I'm going to start by thinking about the area formula for that rectangle, which, if this is an ordered pair called xy, then this is x and this is x, so this whole thing is 2x, and the height here is y. So I've got 2xy. And we know that y equals cosine x. So we can rewrite this as area equals 2x cosine x. And we want to know when this area is a maximum, so let's find a prime. Product rule, 2 cosine x plus 2x times negative sine x. Okay, I guess I can factor a 2 out, and I'll have cosine x minus x sine x equals a prime. Okay, so I've got an a prime, and I notice that I'm suddenly stunned. Yeah, so I know that I need this equal to 0, and I don't know how to solve that equation. Luckily, when I look at my solutions here, they're so decimally, I know that this must be with calculator. So I'll pull out my calculator. Remember, make sure your calculator is set in radians when graphing trig functions. And our function is 2 cosine x minus 2x sine x. Okay, and I don't need the derivative turned on for that. Zoom. Standard. Well, it looks like I've got a bunch of points here, but let's think about this for a second. Remember this bounding curve? Okay, so this is cosine, and this is pi over 2. And this is x equal to 0. And so really I'm just looking on the window from 0 to pi divided by 2 for x values. And lo and behold, I do see a place where a prime goes from positive to negative. If I use my calculator, so I can calculate 0. I get x equal to 0.860335359. So this is where that maximum area occurs. And then they say, what is the minimum shaded area? So let's say, okay, this is, don't shade that in because that's not the shaded area. This is the shaded area. And so what I want to think about now is, now that I know the maximum occurs here when x equals this number, I want to think about this shaded area. I know the full area under the arc of the curve goes from negative pi over 2 to pi over 2 of this function called, of this area function? No, of this cosine curve. That was it. cosine curve. So I'm integrating cosine from negative pi over 2 to pi over 2. That's going to be the full area, but now I'm going to subtract the area minus the area of the rectangle. Okay, so here we've got sine from negative pi over 2 to pi over 2. So sine of pi over 2 minus a minus sine of negative pi over 2, which is 1 minus a minus 1, or 2. So that part is 2. Now what about the area of this rectangle? Well, the area of the rectangle is back up here. It's 2 times this x value times y. Well, what's the y value? It's the cosine at this point. So cosine of 0.8603339, and I get this number. So there's my y, here's my x, times 2 times 0.8603339 times 2. So 2 minus the area of the rectangle, 1.122, and that gives me 0.877. So that's the minimum area, minimum shaded area. This does not ask for a justification. It is a multiple choice problem, and I see that my answer is choice B. Choice B is my answer for number 2. Okay. Ooh, there was thinking there. Now, isn't this interesting? I mean, just to go back for a second, we wanted to minimize this area, so we had to maximize this area. We did an optimization problem to determine when we would have a maximum area. Then we said, okay, if they want to know what is this minimum area, we needed to find the area under the cosine curve from negative pi over 2 to pi over 2. And then we had to subtract this maximum areaed rectangle. We found the area under the curve, and then we found the area of the rectangle by doing 2 times this x value times this y value. We found the y value by plugging this x in here to cosine. And that was our maximum rectangle's area. So 2 minus the area of the maximum rectangle gave us the minimum shaded area. All right, there are some thinking problems in free response. Or multiple choice. Oil is leaking from a pipeline on the surface that forms surface of a lake that forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. Look at those units. They're cubic centimeters per minute. So I think they've given me a dV/dt as 2,000 centimeters cubed per minute. Okay. And what else did they say here? The oil slick takes on the form of a right circular cylinder. Oh my goodness, they actually gave me the formula. Pi r squared h. Okay, so it looks like I have a dV/dt, which means I'm going to need to be taking the derivative of this with respect to time. But I don't particularly want to do it with 2 variables over here. So let's keep reading. With both its radius and height changing with time. Oh, well, I guess they do want me that. The recovery vehicle shows up on the scene and begins removing oil. The rate at which the oil is removed is given by r of t equals 400 square root of t. Okay, so this is the rate at which oil is added, and this is the rate at which oil is removed. All right, what else do we know? We know oil continues to flow at a constant rate. Find the time when the oil slick reaches its maximum volume. Okay, so this is the new way we experience Well, we've often been experiencing optimization in AP questions the last few years, where they give us a rate in and rate out problem. So we want to think about an amount of oil function. And amount of oil function is going to be the integral of the rate in minus the rate out with respect to time. So from 0 to t. There we go, a of t. If I want to know when the amount is greatest, then I want to take the derivative of this and say a prime. So that means I take the derivative of this integral, and I get my rate in, which is this 2000, minus my rate out, which is this 400 square root of t. Okay, so where do we go from there? Well, I set a prime equal to 0, and that happens when 2000 equals 400 root t. If I divide both sides by 400, I can cancel, and I get 5 equals square root of t. If I square both sides, I get t equals 25. So I think when time equals 25, I have a maximum volume. And that is asking me, but they do ask me to justify. So a prime 0, 25. Okay, here's my a prime function. I see a square root over here, so I'm going to choose easy to take square root numbers, like 0. Square root of 0 is 0, 0 times 400 is 0, 2000 minus 0 is positive 2000, so that's a plus. And if I put something in over here like 36, square root of 36 is 6, 6 times 400 is 2400, 2000 minus 2400 is negative 400, and so I get minus. So the amount or volume of oil in the spill is a max when t equals 25, because to the left of t equals 25, a prime is greater than 0, and to the right of t equals 25, a prime is less than 0. Okay, there's problem number 3. A lot of words and not so bad. I just had to integrate rate in minus rate out, and then to find when that amount was greatest, I took the derivative. The derivative of this integral, made for a very convenient algebraic expression, which I then set equal to 0 to find a critical point. Okay, so, there's a little integral there, there's a little FTC part 1 there, but mostly it's a plain old optimization question, where we want to find the maximum of some function. I find it useful to write the equation of that function, in this case, amount or volume. Okay, number 4. The volume of a cylindrical tin can with a top and a bottom is to be 16 pi cubic inches. So we know that V equals 16 pi. And we know that the formula for volume of this cylinder is pi r squared h. So I know at some point I'm going to be setting this volume equal to that number. But not right yet. Let's keep reading. If a minimum amount of tin is to be used to construct the can, what must be the height in inches of the can? Okay, so this then becomes my helping equation. And the one I want to take the derivative of is the surface area. Remember, the surface area, and look, they don't give me the equation for surface area. I actually have to know this formula. It's 2 pi r squareds, one top, one bottom, so I've got 2 of these circles, plus the lateral area of the can, which is 2 pi r h. Okay, so there's my surface area formula. This is the thing that I'm trying to minimize. So I would really like this in terms of one variable, not two variables. So over here, I think I'm going to say that h equals 16 pi divided by pi r squared. Or h equals 16 over r squared. Okay, well I can cancel an r with an r, and then 16 times 2 is 32 pi over r. And then now here we have the 2 pi r squared. So here's surface area. But we want to minimize surface area, minimize the amount of material used. So we need SA prime. So we'll take the derivative here and get 4 pi r. And then the derivative of this is going to be minus 32 pi over r squared. We're wondering about critical points, and clearly radius can't be 0 because that wouldn't be much of a can. So I want to set SA prime, though, equal to 0. 4 pi r minus 32 pi over r squared. I get 4 pi r equals 32 pi over r squared. I'll multiply by r squared and get r to the third equals 8, and so r equals 2. And if r equals 2, then I know here that h equals 16 over 2 squared, or 4. So, volume, does it say dimensions? What must be the height? The height is 4 inches. And they don't ask for a justification when surface area is height of the can is 4 inches when the surface area is minimized. I know, and you're saying, well, you didn't check to see that it's a minimum. So let's check and see. I'm going to put my minimum r here. I mean, it was my only critical point. And yeah, but I'll check my radius equal to 2. So we'll go back to SA prime. Here's SA prime, and we'll plug in a 1. And so I have a 1 here and a 1 here. That's 4 pi minus 32 pi is negative 28 pi. And if I plug in a 3, so here I get 32 pi over 9. This is 36 pi over 9. Oh, 12 pi. 12 is 12 times 9. 108 pi over 9 minus 32 pi over 9. That's definitely positive, and so I know that I have a minimum here. It's good to check just to make sure it confirms that, that really is the place that I'm looking for, and it reminds me, hey, maybe I should check endpoints, but there are no endpoints in this situation. This wasn't a justification problem, so I don't have to write a justification. I move on to number 5. Number 5 says simply enough in one sentence, find and justify the absolute min of f of x equals 2x e to the 2x. So I need f prime, which I find with product rule, 2 times e to the 2x plus 2x, and the derivative of this will be itself, times the derivative of the inside function, 2. I'm going to factor out a 2 and an e to the 2x from both of these. When I do, e to the 2x, here I'm left with 1, not 0, 1, and then the plus sign, and then this 2x. So there's f prime. Well, this is never equal to 0. This is equal to 0. when x equals negative 1/2. So I'll make my f prime sign chart. I'll put my negative 1/2 on. There are no other critical points. Let's just see what's happening here if I plug in a negative 1 and a 0. Okay, so this is always positive. But over here, if I plug in a 0, I get a positive. So positive times positive is positive. But if I put in a negative 1, this is positive. Negative 2 plus 1 is negative 1. Negative times positive is negative. And so then I end up with a min. And it said, find and justify the absolute min. Well, there are no other critical points. There are no endpoints of a bounded interval that can be concerned with. So this min is, in fact, the only min. And so we can write our justification sentence because it asks for one. There is only one critical point, and it's a min because, or on f at x equals negative 1/2, because to the left of x equals negative 1/2, f prime is less than 0, and to the right of x equals negative 1/2, f prime is greater than 0. Since there are no other critical points or endpoints, this min is also the absolute min. Okay, there's number 5. Let's take a look at problem number 6. Okay, speed of a runner in miles per hour on a straight track is modeled by f of m equals 1/10 negative 2m to the third plus 9m squared minus 12m plus 7, where this is distance and this is speed. Okay, what else do we know? What is the maximum speed on 0 to 3? So we want to know when the speed function is a max, and that maximum occurs when we take the derivative here. So f prime of m is going to be 1/10 negative 6m squared plus 18m minus 12. The derivative of this is 0. So I notice that I can factor out a 6. In fact, I can take out a negative 6, negative 6/10, and we get m squared minus 3m plus 2. This factors as m minus 2, m minus 1 times negative 6/10. There's f prime. We can make an f prime sign chart and put 1 and 2 on it. Why did I put 0? Because the runner starts running at time equal to 0. Or this isn't time, this is distance. So they've run no miles yet. At 1 mile, at 2 miles. Okay, so let's plug in some values into this function. If I plug in a 3, I've got a positive times a positive times a negative, which is a negative. If I plug in 3 halves, 3 halves minus 2 halves, that's positive. 3 halves minus 2, that's negative. Positive times a negative is a positive. And if I plug in a 1/2, I get a negative times a negative times a negative, which is a negative. So it looks like minimum speed occurs at 1 mile and maximum speed occurs at time equal to 2 miles. Let's take a look and see what they were asking for here. They were asking on 0 to 3, the maximum speed. Well, this is when the maximum, but what is the maximum speed? Well, I have to take this when, this 2 miles, and plug it in. I need f of 2, which will be 1/10 negative 2 times 2 to the third plus 9 times 2 squared minus 12 times 2 plus 7. Okay, so that's 8, negative 16 plus 36 minus 24 times 1/10 plus 7. So I've got positive 20 minus 24. That gives me negative 4/10 plus 70/10, which is 66/10, or 6.6 miles was the input, and 6.6 in miles per hour. Miles per hour. Okay, so I think my answer to number 6 is 6.6 miles per hour. Now, it does say, what is the maximum speed? It is multiple choice, and so I'm going with B. I'm not going to worry about plugging the 1 in, because that's a min. At 0, I can plug a 0 in pretty quickly and get 7. Wait a second. It's 7. Why can't I plug in a 0? That's an endpoint. And if I plug in a 0, all these go away, and I get 7. 7 is bigger than 6.6 miles per hour. And here it even says, including 0. 7. 7 is the maximum speed. It is not 6.6 with B. It is at when they start running with 0. Oh, that's very interesting. And in fact, I have that. But we should definitely pay attention to the endpoints at bounded intervals. That's what that problem tells me. Okay, problem number 7. 7 says we've got these points that are vertices as shown in the picture, and that's a funky picture. It looks like this, and we've got this, and this, and this. This is 3, 0. This is x, 0. This is x, comma, 1 over x squared. And here we have 3 with the same height as over here, so 3 comma 1 over x squared is that one. Okay, for what value does the rectangle have a maximum area? So I want the area of that rectangle. The length of the side is x minus 3, because this is x and this is 3, so this length would be x minus 3. And the height of the rectangle is this, 1 over x squared. So area equals x over x squared minus 3 over x squared, or 1 over x minus 3 over x squared. Yep. All right, and they want to know maximum area, which means I want to take the derivative of this. So it may be useful for us to write this as x to the minus 1 minus 3x to the minus 2. And so a prime then is going to be negative 1x to the minus 2 plus 6x to the minus, we're subtracting 1, minus 3. Okay, and that would be negative 1 over x squared plus 6 over x to the third. I'm actually going to make a common denominator here. and get negative x plus 6 over x to the third. There's a prime. And a prime equal to 0 when x equals 6. A prime is undefined at x equal to 0, but I know x can't be 0 because x is to the right of 3. So I'm not worried about undefined here. I'm just worried about when a prime is equal to 0. And so that appears to be when x equals 6. Let's make an a prime sign chart and shove 6 on it just to be sure. I know we have to be greater than or equal to 3. So here's our a prime. And if I plug in 3 here, I get minus 3 plus 6 is positive 3 over 27. That's a positive. And if I put in a bigger number here, like 10, negative 10 plus 6 is negative 4 over 1,000. That's definitely a minus. So I have a max at 6. Am I asked to justify? No, it's multiple choice. I see my choice here as C. C is this value. Okay, so let's take a look at problem number 8. 8 says, consider right circular cylinders for which the sum of the height and the circumference is 30. So circumference is 2 pi r plus height equals 30. That has the look of a helping equation if I ever saw one. I'm considering them. What is the radius of the one with the maximum volume? Okay, so volume is the thing I want to maximize. I have a helping equation here. 30 minus 2 pi r. So let's plug that in. V equals pi r squared. 30 minus 2 pi r. And I like distributing here. 30 pi r squared minus 2 pi squared r to the third. We want v prime, so we've got 60 pi r minus 6 pi squared r squared. And we wonder when v prime is equal to 0, because we're looking for a max, pi squared r squared. And I set this v prime equal to 0, which means 60 pi r equals 6 pi r squared. I'm going to divide both sides by pi and 6 and r. And that will give me r equals 10. So it looks like r equals 10. Let's confirm that. V prime 10. Radius minimum is 0. I can't really have a 0 radius for this cylinder. But let's see what happens when we plug in a 10 into v prime. You know, my life would probably be easier if I factored this v prime. So 6 pi r, leaving me 10 minus pi r. Okay, so let's plug in some numbers. If we plug in a 0, no, a 1, I get 10 minus pi, which is a positive number, 6 point something, times a positive. So positive times positive is positive. But if I put in something here like 20, this is still positive, but now I've got 20 times pi. And 20 times pi is going to be much bigger than 10. And so this is negative. There seems to be something wrong with this, because that shouldn't be 10. I got 10, so I'm wondering, did I factor in properly? No. Yeah, I think something's happening back here. I think it's back here. Let's go back here and check for a second. Oh, look at that. Look at that. Right? I left off that squared. I need to cancel one of them, but one of them is left. I need to divide by pi. So this is 10 over pi, not 10. 10 over pi. That's much better. Okay, so now when I plug in numbers, 1 still works, 20 still works. Those are great. That's perfect data, but I have a new critical point, and I feel much better about 10 over pi, especially when I see it as my answer E for this multiple choice problem. Okay, let's take a look at problem number 9 now. Problem number 9. Ooh, so many pieces of paper. Okay. Nine says, consider all the lines in the xy plane that both pass through the origin and the point xy, where y is equal to x squared minus 4x plus 9 on 1 to 4. Okay? And our line has to pass through the origin. Whoop. And so there's x, y. Okay, so what about this? The figure below shows one such line. Which of the following statements is true? The line with the minimum slope passes through the graph of. Minimum slope. Well, so I sort of feel like this one, I need to minimize the slope formula. And what is the slope formula? Well, the slope formula is y minus 0 over x minus 0, because we have to pass through 0, 0, or y over x. Hey, and look what y is. It's x squared minus 4x plus 9 over x. So here's my slope equation. In fact, I might even want to split this into 3 fractions and get x minus 4 plus 9 over x. This is slope, and now slope prime, to find the smallest slope, 1, derivative of that is 0. The derivative of that is minus 9 over x squared. And when is m prime equal to 0? Well, I got 1 equals 9 over x squared, or x equals 3, which is on that. Now, I see at x equals 0, slope is undefined, but that's also outside my boundary, so AP is making it so I don't have to worry about this undefined derivative at all. So I've got an m prime sign chart, and I want 1 and 4 and 3 on it. 1 and 4 because they gave me a bounded interval. So let's plug some values in, like 2. That would be 2 squared or 4. 9 divided by 4 is 2 1/4, which is going to be negative. And if I plug in something bigger, like 4, I'm going to have 9 over 16, which is less than 1. 1 minus less than 1 is a positive number. So I can see that I have the minimum slope when x equals 3. And look at our choices. All of these y's are the same, and all that's different are the different x values, and we want choice C at x equals 3. Okay, choice C for number 9. Well, there are only 11 questions on here, so we only have 2 more to do. Let's take a look at problem number 10. 10. Figure below, side length is 40. It's a square. Cut up into pieces, the white part's discarded. I guess we need to start by writing the formula for the volume of this box. And this box, unlike many of the ones that we did in pre-cal, This box has, in fact, a top to it. That top doesn't affect the volume per se. It does affect the surface area. But if I'm thinking about cutting out x by x from each of these, and this is 40 long, and this way, point, and this is 40 over here, and we're going to fold along that dotted line. Okay, so there's the bottom, there's the front, there's the back, left side, right side, and top. And we're keeping all of this, and we're throwing these little bits away. And you know this is x by x. Okay, so I don't know how big these are, but I know they're the same because they're the top and bottom lengths. So I'm going to say that this side length, 40, equals 2 question marks plus 2 x's. And I'm solving for question marks, so 40 minus 2x equals 2 question mark, or question mark equals 20 minus x. So this is 20 minus x. This is 40 minus these 2 x's, and the height is x. So the volume is x, 40 minus 2x, 20 minus x. Okay? Which of the following statements must be true? And we're talking about all minimum or maximum volumes. So I need to find the derivative of this, but I think it's worth at least some distributing, if not some foiling. So v equals 40x minus 2x squared. And here, 20 minus x. To FOIL or not to FOIL? Well, if I don't FOIL, I'm going to have a bunch of factoring, and if I do FOIL, I'm going to have some factoring. So I think I'm just going to use the product rule and say that v prime equals 40 minus 4x times, maybe I wanted to FOIL, plus negative 1 times 40x minus 2x squared. Okay, so I've got a FOIL here. I'm going to go back and FOIL here. V equals 800x minus 40x squared minus 40x plus 2x to the third. Can I combine like terms? Yes, I can. And so v equals 760x minus 40x squared plus 2x to the third. If I take the derivative of this, I get 760 minus 80x plus 6x squared. Okay, well, that kind of sucks. Now I wish I'd done it the other way, because I would have had some maybe common factors to factor out. Can I factor out a 2? Ooh, yes. Wow. I don't know if I'm allowed a calculator, but I kind of think that I'm not allowed a calculator on this problem. Yeah, I guess I'm gonna go back a second time. Sorry, everybody. V prime 40 minus 4x times 20 minus x plus negative 1 times 40x minus 2x squared. Okay, so I've got these two terms, and I'm looking to see what, if anything, I can factor? Well, I can see I can factor a 2 out of each of these. And so I've got minus 2, 20 minus, oh, and an x. I can take that x out. 20 minus x. And over here, I have a 20 minus x. And I can factor out a 4 and have 10 minus x. Well, that doesn't get me much, but this does. So I can pull out a 2 and a 20 minus x, and I'm left with a 2 here because I took out 2, and this 10 minus x, this minus sign. I took out this, I took out the 2, the x is still there. So I have 20 minus 3x times 20 minus x times 2. There's v prime. Okay, so what critical points do we have? We got when v prime equals 0, we get x equals 20, and x equals 20 thirds. So, v prime sign chart, we'll plug in 20 over 3, and we'll plug in 20. 20 divided by 3 is a little bigger than 6, so I'm going to be safe plugging in a 10 and a 5 into v prime. Here's a nice factored v prime to plug numbers into. If we plug in a 5, this is positive. If we plug in a 5, this is positive, and so I get a positive here. If I plug in a 10, though, 10 times 3 is 30, 20 minus 30 is negative, times a positive, and that's negative. So it looks like maximum volume occurs when x equals 20 thirds. And what do we see for choices? Maximum volume 20? No. Maximum volume 20 thirds? Yes. D is my answer for this problem. D for number 10. Okay, and now finally number 11. It looks like it's got a bunch of parts. It has all the feel of a free response question. So let's not expect all of it to be optimizing. Let's see what they have. Says no calculator. The number of gallons of olive oil in a tank at time t is a twice differentiable function. That means I can take the derivative of a and take the derivative of a prime, and that both of those exist everywhere. There's no undefined derivatives, either first or second. We also know that a prime and a double prime are continuous. Well, yes, I know that both of them. Well, I know that a and a prime are continuous everywhere, where t is measured in time from 0 to 35. Okay. Values of a of selected times are given. Okay, so a is in the table. And then part A. Use the data in the table to estimate the rate at which the number of gallons of olive oil in the tank is changing at time equal to 10. So I want the slope of, or rate of change of A at time equal to 10. But I notice that 10 doesn't show up on this table. I have values on either side. And so what I'm going to do is say that A prime of 10 is approximately the average rate of change, A of 15 minus A of 5 over 15 minus 5. Okay, so A of 15 is 25, A of 5 is 18 over 10. And we end up with 7 over 10, and those are gallons on top and hours on the bottom. Use the data to estimate the rate. There's my estimated rate for part A. No justification needed, just the work shown. B. B says on 0 to 30, ooh, look, a different boundary than the one they gave me before. Pay attention. Okay, it says, at which time will A prime equal 1/5? Justify your answer. Okay, so A prime is the slope of A, and I'm looking for a specific time on 0 to 30 when the slope oh, is there a time? You know, it's really good to read the question. Is there a time when the rate of change is 1 gallon every 5 hours? Well, you know, I think this might be I think that this might be an IVT problem. We know that A and A prime are continuous because A is twice differentiable. I just want to point out that in prior years you didn't have to make this statement, but starting last year you need to make this claim before using something like IVT. So I want to think about A prime of 30, and I want to think about A prime of 0. Can I think about those things? No, of course I can't think about those things, because I've got, I was hoping to say, according to IVT, I must pass through all the slopes, all the A primes from this A prime to this A prime, and that this one would be in between. But I don't have a way of finding exactly these values. You know, I could kind of approximate them on one side. But I think instead, since I don't have A prime values, but I do have A values, I actually want to use MVT. And MVT says A prime of C equals A of 30 minus A of 0 on 30 minus 0. So A of 30 is 16, A of 0 is 10 over 30, and we end up with 6 over 30, or 1/5. Aha! So A prime at some point equals 1/5. According to MVT, we are guaranteed, because we've met the preconditions. What were those preconditions? The function is differentiable. We were given that. And we have to state that the function is continuous, that A prime is a continuous function. That's why they told us twice differentiable. Not only do I want to know that A is differentiable, but I also want to know that A prime is continuous. And I get that by knowing that A is twice differentiable. I have to make both of those claims in order to use MVT here. So, what do I have? I have A prime is both continuous and differentiable. Please write that down. In fact, I'm going to write that down. I'm going to change markers and take the strident red, A prime, because A prime is both continuous and differentiable on 0 to 30. MVT says there must be at least one point where A prime equals 1/5. See my work here. Okay, so there's my answer to part B. Let's take a look at part C. Part C says the number of gallons is given by G. G is a function of time. 5t minus 2/3 t plus 9 to the 3/2 plus 28. Okay, that's the number of gallons. That's an amount function. That's not a rate function. The number of gallons where t is back onto 0 to 35. And then they say, based on this model, when is the number an absolute max? Okay, so I need G prime. which is 5 minus, I take the derivative of this, which means I bring down the 3/2, and that cancels with the 2/3. So I've got t plus 9, subtract 1, 1/2. Derivative of the inside function is 1, and the derivative of this is 0. So set g prime equal to 0. So 5 equals the square root of t plus 9, or 25 equals t plus 9, or t equals 16. So on my g prime sign chart, I've got 0, 35, because they gave me a bounded interval, and I've got 16. So let's plug some values into g prime. I like plugging in 0. Square root of 9 is 3. 5 minus 3 is a positive. And if I plug in something over here, what number plus 29 makes 36? Is that 27 plus 9? So if I plug in a 27, plus 9 is 36. Square root of 36 is 6. 5 minus 6 is negative. And so I have a maximum here. It's absolute maximum, though, and so I kind of feel like this is a candidate's test problem. I may not be, but I sort of feel like I need to treat this differently than if they had just said there's a maximum. When is there a maximum? They want absolute maximum. And I know you're tempted to say, well, this is the only max because both of these are mins. That might be sufficient, but some years it's not, and they really have enjoyed recently the candidates test, where you show them g of each of these possible candidates by plugging these times back into the original g function. So if I plug in a 0, square root of 9 is 3. 3 to the third is 27 divided by 3. 27 divided by 3 is 9 times 2 is 18. So I got negative 18 plus 28. I get 10. If I plug in a 16, though, 16 plus 9, oh, well, that works. I get 25. Square root of 25 is 5. 5 to the third is 125. And so now I'm looking at 80 minus 250 over 3 plus 28. So that's 108. 108. And if I need a common denominator, that's 324 over 3, which is going to be 74 over 3, which is greater than 10. All right, and so what about 35? 35 plus 9 is 44, and I don't know the square root of 44. So, yeah, you know, I'm okay writing this down, but I don't think they intend me to minus 2/3 44 to the 3/2, and I'm hoping that this number is in fact smaller than 74/3. I mean, I know it is because this g function is decreasing until we get to 35, but you know, they really have enjoyed the candidates test recently, so it's probably worth our time to highlight that here. Okay, and so what about part D? Part D, the last question, the function g defined above, locally linear approximation. Hey, that's a key word for thinking about tangent line. Build the tangent line at t equals 7 used to approximate g of 8. Is this approximation overestimate or an underestimate for the value of g of 8? Okay, and is used. Oh, look at that. They don't actually need me to find. It doesn't actually say find g of 8. It just says to determine. It just says to determine if this estimate is going to be an underestimate or overestimate. Wow, I could spend a lot of time building that tangent line, and plugging 8 into that tangent line to get an approximation of g of 8. But I don't need to do that. I just need to figure out whether the tangent line is an overestimate or an underestimate in part D. So remember, if we have concave up, our tangent line is an underestimate of the actual value. See, tangent line is below the actual value. But if we have a concave down function, then our tangent line produces values that are actually larger than the original function values. So what we need to do is to find out if this function is concave up or concave down at t equals the point of tangency, which was 7. So I'm looking for g prime of 7. No, not g prime. I want to know g double prime of 7. So g double prime of 7. Let's start with g prime of 7. Here's g. So g equals 5t minus 2/3 t plus 9 to the 3/2 plus 28. G prime, which I believe I did earlier, is 5 minus, oh yes, I did this, to the 1/2. But we need g double prime. Derivative of that is 0. We get minus 1/2 t plus 9 to the minus 1/2. Okay, and if we plug in a 7 here, I get 1, 2, square root, 7 plus 9 is 16. That's a negative number. And because g double prime of 7 is less than 0, we know g is concave down at t equals 7. So the tangent line approximation of g of 8 will be an overestimate. We have an overestimate. All right, and that's all we had to do for part D. I hope this was a helpful video in going through these problems. These are the new types of optimization problems that AP wants us to be comfortable with and able to focus on. So get cracking, practice. You might want to do these more than once.